Hi, for this recording, I'm going to show you how to do 7a and 7b. 7a to show that vector 1, 1, 1 and 1 minus 2, 1 are perpendicular in three-dimensional space. Let's look at how I do this part. So I have vector 1, 1, 1 is v1 and vector 2 is 1 minus 2, 1 is v2. Now, to show that they are perpendicular, in this case, the easiest way is to do the dot product. So we know that v1 dot v2 is, in many ways, is equal to 1 times 1, you get 1, and 1 times minus 2, you get minus 2, and last term, 1 times 1, you get 1. So when you add them up, this is a dot product of these two vectors, you find that this is 0. So when the dot product between two vectors is 0, we know that v1, these two vectors are perpendicular. So v1 and v2 are perpendicular. If you have v1 and v2, if the angle between them are theta, we know that v1 dot v2 will be just the length of v1, the length of v2 cosine of theta. Therefore, if the theta is 90 degree, then the dot product is 0, since we know that if degree, you should expect that v1 dot v2 equal to 0. This is how we answer the first part. Now let's look at the second part, which is slightly harder. Now we need to understand the question of second part. So in this second part, let's look at the question again. Suppose u is the point 1, 0, 0. Find a third vector v3, which is u minus u cap. And this v3 is perpendicular to both v1 and v2, and u cap lies in span of v1 and v2. Let's try to understand the question first. So what is the span of v1 and v2? So in this case, so I have a v3. So suppose this is a span of v1 and v2. Now the span of v1 and v2 is a plane because v1 and v2 are 3D vector. So the span of this two vector will be a plane path to origin. Here is a v1, somewhere here is a v2. So v1 and v2 are lying on the plane spanned by these two. And now I have another vector in space, the vector u in space. And then this u can be decomposed into two parts. One part, you can find that it is lying in the span of u1 and v2, it's called u cap. Another part is u minus u cap. This is the v, and v will be perpendicular to the plane spanned by v1 and v2, and this is what we want to find. We want to find a v cap and u. That means that v is equal to u minus u cap. Now, how do I find u cap? If you know how to find u cap, then you know how to find v. Now, let's look at the result from David Ley. David Ley says this. This is what we call the orthogonal decomposition theorem. If W in a space of Rn, subspace of Rn, and for each y in Rn can be uniquely represented in the form of y equal to y cap plus z. And what is y cap now? Y cap is in W, and z is W perpendicular. In fact, if you u1 and up is any orthogonal basis of W, then y cap is y is a combination of u1 to up according to this dot product, using this dot product to find, and z will be just y minus y cap. So in this case, if you look back, where is my v1 and v2, since v1 and v2 are orthogonal. So the space in this case is this W here. W will be the span of V1 and V2, and we know that V1 and V2 are orthogonal because their dot product are 0, as V1 dot V2 equals 0. Therefore, I can find out what is V now. The V is equivalent to Z in the decomposition theorem. So how to find U cap? So U cap, in our question, U is 1, 0, 0, as the questions tell you that, and U is 1, 0, 0. So I'm going to use it to find my U cap now. So V1 is 1, 1, 1, V2 is 1 minus 2, 1. So I can take V1 is 1, 1, 1, V2 is 1 minus 2, 1. So U cap in this case, the vector lies in the span of W. In this case, will be U dot V1 over length of V1 square, V1 dot V1 multiplied by V1 plus U dot V2 over V2 times V2. Now you can do this provided V1 and V2 are orthogonal, alright? So note that as V1 and V2 are orthogonal basis for W, right? For W, which is a span of V1 and V2. Then we can do this. So where is U1, U dot V1? So let's try to figure out where is U. U is 1, 0, 0. V1 is 1, 1, 1. So U dot V1 will be equal to, based on the calculation, 1 times 1, you get 1. And then plus 0 times 1, you get 0. And 0 times 1, you get 0 again. And so U dot V1 is 1. How about V1 dot V1? V1 dot V1 in this case is actually 1, 1, 1 dot 1, 1, 1. So follow the argument as before. 1 times 1, you get 1. And the other component, 1 times 1, you also get 1. And the third component, 1 times 1, you get 1 again. So V1 dot V1 is 3. Then we also need to do U dot V2. So U is 1, 0, 1, 0, 0. V2 is 1 minus 2, 1. So U dot V2 is equal to 1 times 1, you get 1. And the rest are 0 as the same as before. You get 0 and 0 based on the other number or 0 here. And we want to find out what is V2 dot V2 is equal to 1 minus 2, 1 dot with 1 minus 2, 1. So you get, in this case, 1 times 1, you get 1. And minus 2 times minus 2, you get 4. And 1 times 1 in the third component, you get 1 again. So total you get 6. Therefore, U cap is equal to U dot V1 over length of V1 square, which is V1 dot V1 times V1 plus U dot V2, V2 times V2 dot product and V2, alright? So U cap in this case is U dot V1 is 1, V1 dot V1 is 3, 1/3 of V1, alright, 1/3 of V1, V1 is 1, 1, 1, and U dot V2 V2 is 1 also, and V2 dot V2 we got 6, and V2 is 1 minus 2, 1. So if you do this, U cap in this case is 1/3 times 1, or 1/3, 1/3, plus 1/6 minus 1/3 and 1/6. So 1/3 plus 1/6 is what? Half, 0, half. So U cap is half, 0, half. This is in the span of V1 and V2 as a combination of V1 and V2. Now I want to find out what is V now. So V is U minus U cap. In this case, U is 1, 1, 1, 1, 0, 0. U is 1, 0, 0. U cap in this case is half, 0, half, as we find out. So this is equal to half, 0, minus half. So notice that we find a vector v now. So the situation is this. We have the plane W, which is a span of v1 and v2. And we have a vector u here in space. And this vector u can be decomposed into two parts. The part on the plane is called u cap. The part perpendicular to the plane is called v. And we have found out both u cap and v now. U cap is equal to half, 0, half, and v is equal to half, 0, minus half, where u is 1, 0, 0. 1 is equal to 1, 1, 1. V2 is equal to 1 minus 2, 1. That's the end of the recording.